There we go. Let me begin with a word of prayer. So, Heavenly Father, we thank you for this day. I again thank you for these students, and just pray you'd help us to understand a little bit more about Lebesgue integration today, and just that you be glorified in what we do. In your name I pray, Lord Jesus. Amen. Okay, so we talked about step functions last time, and we ended by describing the idea that you can take a function and represent it by some sequence of step functions that, the series of, add those things together and you somehow represent the function. And if that's possible, such that the absolute value, of this summation is finite for every x in the domain, which, and we're just talking about the domain being all of R here at the moment. Then it's said to be, Lebesgue integrable, and you define the integral by, how do we define the integral? Remember, the integral of such an f was just equal to the corresponding integral of the step functions, right? We just add together the integrals of the step functions. And the integrals of the step functions, well, those we actually defined last time in terms of basically just, areas of rectangles, right? So, yeah. All right, so let's look at lemma. Lemma 2.3.2. And here's what it says. It says if f is, let's say, represented by the sequence f1 plus f2 plus da 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 da, and f is non-negative, then the integral of f1 plus the integral of f2 plus da 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 is greater than or equal to 0. Also not negative. All right, so this is the lemma. I'm going to try to follow his proof and see if we can make sense of it, okay? So here we go. So proof, let epsilon be greater than 0 and n not a natural number, such that the sum n equals n naught plus 1 to infinity of the integral of the absolute value of fn is less than epsilon. All right. Now, okay, so there's a lot packed into the notation, right? So this notation right here, this presupposes f is, let's say, Lebesgue integrable, all right? So that means, among other things, that the limit of this, as n goes to infinity, from n equals 1 to infinity, is less than infinity, right? That was an assumption of the definition, and so if the limit of the series is less than infinity, well, that means it's a natural consequence of that if you go far enough out in the summation, right, you can make the tail of that series as small as you like. If this were not the case, it would contradict the fact that the sum from n equals 1 to infinity is less than infinity, right? So this is a reasonable starting point, I think. Yeah? All right. What next? He says define Gn equal to the sum f1 plus all the way up to f sub n naught, and then plus the absolute value of fn naught plus 1 plus dot 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 plus the absolute value of f n naught plus n. Weird, like what? Okay, then what? He says for n equals, he says, since Gn is a non-decreasing sequence of step functions. Why is Gn a non-decreasing?
Is it because it's in starting at in not plus 1? So everything we're adding is greater than or equal to 0?
Oh, well, I mean, this is true, right? I mean, fair enough. This is manifestly positive, right? Oh, this is manifestly non-negative, right?
Yeah.
That is true. And more than that, that piece is less than, well, I can't say it's less than, I mean, excuse me, that's not less than epsilon. The integrals of the absolute values is less than epsilon, but. Why is that the case? Why is this a non-decreasing sequence of step functions? I mean, we have the assumption that f is greater than or equal to 0, right? I mean, we have this, that this is something we're given. It's probably related to that. I assume what this means is that, f of x is greater than or equal to 0, right? For all x in the reals. That's the meaning of that, yeah? Oh, I'm being dumb. This is obviously true. Look, this is dumb. This is really dumb. What happens as you increase n?
You get closer to f.
What's that?
You get closer to f.
Closer to f. That's true. But you're doing what? You're just like you're not. This stays the same, right?
Yeah.
So. I'm just dumb, guys. I'm just dumb. What would g of n plus 1 look like? It would be what? G of n plus the absolute value of f n naught plus n plus 1. Right? That's it. The n is just figuring into the last term. So of course that's increasing. It's non-decreasing because this term could be 0.
So the sum doesn't include the things before the absolute value. The sum is sequence.
Right. Well, yeah, the sequence is defined in terms of this sum.
Yeah.
And the n is only influencing the very last term in some sense. So like the next one is just the last one plus thing. So of course, this is going to be greater than or equal to Gn, right? Which gives you that it's a non-decreasing sequence. It could be equal, Could be constant for some n. All right. So we have Gn is a non-decreasing sequence of step functions. And then what? Such that what? He says such that the limit as n goes to infinity of Gn of x is greater than or equal to 0 for all x in R. Why is that true?
Well, once they contradict the, you get
Let me point out something that's really, like, that makes this totally obvious.
Is it because, like, the left side, f is going to be greater than 0, and you already said that the other side's manifestly greater than 0? So
It's, so yeah, I mean, it's, well, we know that the sum of these is greater than 0, right?
yeah.
And then we're adding together these, which are manifestly non, all right, so my larger point is just this. This is greater than or equal to Fn. Well, Fn not plus n, yeah?
Yeah.
See, because, well, that's not what I mean. Sum k equals 1 to n naught plus n of f sub k, right? So if gn is greater than or equal to that sum, and we know that as the limit as n goes to infinity, that sum becomes f, right? And we know that f is positive, then basically taking the limit, if we take the limit of this as n goes to infinity, we get, you know, the limit. Now I'm starting to feel like I'm spending too much time on this lemma because it's actually really obvious. But gn of x, well, that's actually, you know, greater than or equal to the limit as n goes to infinity of the sum k equals 1 to n naught plus n of fk, right? Also known as f, which is given to be greater than or equal to 0. So, I mean, this is fine. Adding the x's. This is x here, and there's an x here, and greater than or equal to 0 for all x. Okay, great. All right. So then what? He says then we have then this implies that the limit as n goes to infinity of the integral of gn is greater than or equal to 0 by corollary 2.27, which I think we talked about last time. And I literally just mean talked about. I don't know if we actually proved it. I don't think we proved anything last time. But I think that was the that one was the one that followed from the more the deeper theorem, which was theorem 2.26, and then that's a corollary to that theorem. And that the corollary literally just says for a non-decreasing sequence of step functions whose limit is non-negative, that implies that the integral is non-negative. The integral of the sequence is non-negative, which is what we're doing here. All right. Thus, all right, finally, here's the punchline. 0 is less than or equal to integral of f1 plus plus integral of fn naught. All right. Plus the sum n equals n naught plus 1 to infinity of the integral of the absolute value of fn. And then what you do? First of all, why is that true? I think that's that's literally the integral of gn, isn't it? You guys see that? Like, the integral of gn is this, I think. And I think he's taking the limit. He's taking the limit as it goes to infinity. So I should include the limit in my color coding here. But anyway, Then what? What's he do? Well, then his next move is to say this is less than or equal to the integral of f1 plus dot 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 plus the integral of fn naught plus, all right, some funny business here, the sum n equals n naught plus 1 to infinity, all right, parentheses fn, integral of fn plus the integral of the absolute value of fn, all right, plus, what is he doing? Why is he adding all this stuff? Plus the sum n equals n naught plus 1 to infinity of the integral of fn sneaky. Do you see why he can do that? So, can you see that, Audric? I don't know.
Where you add double FM.
Yeah, it's a little sketchy here. So this right here is exactly what we had above, right?
Yeah.
This term right here, why is it okay to add that? I mean, it's not an equality here. It's a, inequality. Think about this. So the step function, right? It's either positive or it's negative, right?
Yeah.
So if it's positive, this is just the integral of twice the absolute value. And if it's if it's negative, they're canceling. So you're either adding something or it's adding 0. So that's definitely, yeah, you've done. You've done nothing, except that you've done something, right? Because if you look at this, lo and behold, all of this right here is exactly. Oh, that's F.
Okay, yeah.
That's F. Because remember, F is the sum, the integral of F rather, I should say. It's not F, it's the integral of F, because the integral of F is the sum of the integrals of the steps which represent F, so that's integral of F. But then you've got this other piece over here, plus the sum n equals n naught plus 1 to infinity. And you got two of these dudes, so integral of twice the absolute value of fn. Yeah. But I think at this point, you can go back into our initial assumption about the construction of n naught and see that that piece is what? Right, that's less than 2 epsilon, right? So, yeah, less than or equal to integral of f plus 2 epsilon. Actually, he hasn't written the integral of f there. He's just written the, I mean, he's not, fine. Fine. The sum. Maybe you forgot what we're trying to prove, and I'm assuming the point by writing that. I don't know. Integral of fn, right? All right, great. All right. What was this? What we're trying to prove? That the sum of the integral is greater than 0.
It's just since epsilon, like Audrey was just saying, since epsilon is arbitrary, then we add it.
Oh, and
Because that whole string is 0 is less than equal to the sum plus 2 epsilon, but epsilon is arbitrary, so we can bring that whole term in this.
Yes, I got it. Yeah, okay.
Yeah. Yes, that's it.
what's that proof?
I was trying to get from the inequality to equal, and I was being tested to see that was n equals n naught plus 1. So when you take this up, n naught, you just keep going, and then there you go, you get the plus 2.
Yeah.
So, yeah.
What?
Okay.
So we're trying to prove then the integral, the sum of the integrals is greater than 0.
Yeah, very greater than 0, yeah.
So we have 0 is less than or equal to the sum of the integrals
Which is what, plus 2 epsilon. So
plus
that's
2 epsilon.
arbitrary.
Oh,
It's just,
that,
remains arbitrary, so you can just take it down and it's
I see. That,
0 is less than or equal to the sum. Yeah.
right, so that does imply that the sum has to be positive, yeah.
Right.
Because if the sum was negative, you could get a contradiction from this, right? Yeah. Like if somehow the sum,
If the sum is negative, then
if the sum,
contradict the inequality we have.
yeah, exactly. That wouldn't gel with what we have here if you,
Yeah, if the sum was negative, that means epsilon would be negative.
Yeah.
right. Yeah, so just to be concrete, if this sum was minus 0.1, then I could go through this argument and put, 2 epsilon to be, I could put epsilon to be 0.1.
Yeah.
And then I'd have minus point, I mean epsilon to be like minus point, let me say this is equal to minus 0.5. I could make the epsilon equal to epsilon equal to 0.1. Then at minus 0.5 plus 0.2 would be equal to minus 0.3, which is less than 0. Wait a minute, what? Minus 0.3 is greater than or equal to 0, rather, which would be, right, ridiculous. Okay, sorry. So, yeah. All right, so I think the next one is perhaps more interesting. So the next one is corollary 2.33, which says that if f is represented, I'm just using the term represented by this series of functions, step functions, of course, Fn, and f is also represented by another sequence of step functions. Maybe I should say series of step functions since we're adding them together. I don't know what the right language is here, guys. Then the sum n equals 1 to infinity of the integral of Fn is equal to the sum n equals 1 to infinity of the integrals of Gn. In other words, what this corollary says that if you have a function which is represented by two different sequences of step functions, then the Lebesgue integral that they generate is identical. Because the way we calculate the Lebesgue integral is to add together the step functions like this, right? So this would say that the Lebesgue integral is independent of your representation of step functions. So let's prove this thing. He says, since 0 is represented by f1 minus g1 plus f2 minus g2 plus ... First of all, do you believe that?
Yeah, they sequence the same thing. It should.
Right. F minus f is the 0 function, and so it follows that this sequence limits to the 0 function because they both separately limit to f. Okay, fine. Then by lemma 2.32, what's that give us? Oh, wait a minute. How does lemma 2.32 apply? So this is greater than or equal to 0. That's clear? I guess that's clear, right? Yeah. So we have what we need to apply lemma 2.32 then. So then we have that the integral of f1 minus the integral of g1 plus the integral of f2 minus the integral of g2 plus dot 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 greater than or equal to 0. Okay, and then basically for, I mean, you can be more careful with this. You could do this to a finite value, like do a finite sum, and then you could rearrange and get the difference of the finite sum of the integral, f integral, and the finite sum of the g integral. He just goes straight to the series result, which is that the sum n equals 1 to infinity of the integral of fn then minus the sum n equals 1 to infinity of g integral of gn is greater than or equal to 0. So if I call this thing big F, and if I call this thing big G, then what this tells me is that F is greater than or equal to G, right? But this argument is symmetric in the role of F and G. You can just as well do the argument with F and G reversed. And so like similarly, likewise, we can prove that G is greater than or equal to F. Or if you like, F is less than or equal to G, right? So therefore F is equal to G, which is what we're trying to prove. So, cool.
Wait, you have a comment on the finite sum? I don't know if that works with the finite sum.
Well, I mean,
Because, like, if they just limit, essentially, to whatever you're trying to find. They don't actually, so, like, if you go to the finite sum, that might not be as clear there.
well, I think that's what this is notation for. It's a notation for the limit of the sequence of partial sums, where I'm talking about the partial sum formed by like, k equals 1 to n of, f sub k. And then you take the limit as n goes to infinity, and we write this is equal to that. That's, that's all I'm saying. It's not, yeah. It's the usual, what do you mean by a series discussion? Well, we mean the limit of the sequence of partial sums, All right, he says corollary 2.33 implies that step functions are integrable. And that in this case, integrals in definition 2.21 and definition 2.31 are equal, which justifies the use of the same symbol in both cases. All right. He says it can be proved in section 2.10 that every Riemann integrable function is also Lebesgue integrable, and that both integrals are equal. All right. The space of all Lebesgue integrable functions on R is denoted by L1R. And the remainder of this book, Lebesgue integrable functions are simply called integrable. So by default, integrable in this book here on out means Lebesgue integrable. So if he wants to talk about Riemann integrable, he's going to say Riemann integrable, right? Okay. So let's take this new definition out for a spin. What's our next theorem? Theorem is that L1R is a vector space. So L1R is, what is it? I just said it a second ago here. It's the space of all Lebesgue integrable functions. All right. Uh-oh. Did you move the camera over?
Oh, crap.
No, it's fine. It's really, it's okay. I just thought of it. Yeah, it's okay. I think it's fine. This argument actually was like a lot easier than the other one, so Anyway, well,
Yeah, no, sorry,
no, you're fine. My wife has criticized me for asking students who are taking the courses to do the videoing because she's like, they have to take notes. How can they take notes and do the camera? I'm like, I know it's not a perfect system, but it's not a perfect system. It's just the... So I mostly tried to do the camera work at UWA, and it usually went badly. Theorem 2.34, L1 of R is a vector space. And integral is a linear functional. On L1R. Moreover, if f and g are in L1R and f is less than or equal to g, then guess what? The integral of f is less than or equal to the integral of g. All right. So here's the proof. Put down my paper for a second, see if we can think through this one. So we're assuming that f and g are Lebesgue integral, right? That means that they're both represented by a sum of step functions, right? So and likewise g. So then f plus g is going to be what? Well, we'd like to claim that that's the same as, you know, so what I'm claiming is that we can add two functions in here by simply adding their their step functions. And notice that that works out because if we think about the what was the condition needed for it to be Lebesgue integrable? Remember back to the definition I wrote last time? You need that the the sum of the integrals of the absolute values is less than infinity, right? So this means